Those of you on phone, remember to pin my screen or my image so that you can see it fully. Okay, so we'll begin. Today's lecture, we'll be looking at how we measure the elements, or rather how we can tell the size of each of the elements. Now, remember we said that the equivalent circuit looks like that. We gave all the details of this equivalent circuit, whereby we have all the items that are listed there. So we had elements being, or rather representing various parts of the circuit, or various aspects of the motor. So we said that up to around this point, this represents the stator. And on this other end, this represents the rotor. And also we said things like, we have stator copper losses, and the power in comes from that side. We had this as core losses, and we had this at the end as air gap power. And we also noted that air gap power is given by, it includes rotor copper losses and converted power, right? So now we want to look at how do we determine the properties of a motor, or rather how do we get the equivalent circuit given a physical motor. So like your three-phase induction motor would look something like that, whereby you would have your motor as a standalone, and you have your stator and the rotor. Now, the only connection that you would have to this device is through your power input, or your voltage input, right? We can assume that you can measure the voltage, the current, the frequency at this point, right? Those are the main elements that you can look at if you have a physical motor. You would want to get the items that you have. So you have your elements, the resistances and the impedances and so on and so forth. You want to get all of those. However, you are mainly restricted to certain aspects of the motor itself, which is you can control the voltage, the current, the frequency that you put in, and you're able to measure these with the rotor, with the equipment that you would have. You can also, to some degree, probably measure the speed of the rotor shaft. That is the actual mechanical speed, which we call N, right? Now, given the voltage, current, and frequency, you would also be able to get various other elements. Some of the powers you can get, for example, input power. You could also get synchronous speed. You could get various aspects like that, okay? Now, bearing in mind that the stator is not physically connected to the rotor, one of the easiest elements of the circuit that we'll be able to obtain is R1. R1, remember, was the resistance of the stator.
Excuse me, sir, could you be a little bit louder?
Oh, the volume is low. Just a second. Let me see. Is the volume low for everyone? Can you hear me better now?
Yes.
It's better
yes.
or it's the same? You okay?
Slightly
Oh.
better.
So, try and see if I can increase it. I think that should be better. Okay, so we were saying that one of the easiest ones you can get is the stator. So that is the resistance of the stator, which is here. Okay. How do you do that? You already know that the stator itself, the windings that are inside here, are directly connected to these outputs that you have. Okay. So it would be a simple matter of establishing the resistance using even something like a multimeter or something like that. However, in order to determine these elements, we have various tests that we can carry out. Just a second. We have various tests that we can carry out, and the three tests that we'll be looking at today are as follows. So we have, first of all, a DC test. Second, we will have the no load test. And third, we will look at locked rotor test. Okay. These are tests that are carried out with the limitations that we've said here, that you can only see the rotor with regards to its physical speed and the voltage input and frequency that you're supplying to the stator. Okay, so we'll look at those in turn. Question? Okay, so let's get started. So the first one is the DC test. So the DC test setup is as you can see. So we have, for all of these tests, we will be assuming that you're connecting to the stator. So this symbol or this part of the circuit that you're looking at is considered to be the stator. Now, what happens with the DC test is that you will apply a DC voltage to the windings. Now, in this case, the windings, you can see, are connected together in a star formation. So the ends of one side of each of the windings are short-circuited together so that you are able to get a supply from one end through to the other. Okay. And you will notice that the circuit or the supply is given through one of the windings and out one of the other. Let's call this winding A, this winding B, and this winding C. Okay. You have two of them connected to each other through the supply voltage that you have given already. Okay. Now, apart from that, this is a standard resistance measurement system. Note that because we are supplying DC, yeah, we are giving it a DC voltage. That means that in the equivalent circuit, if you supply a DC, we have only supplied up to or including this point. Okay. The reason for that is this arm here, remember, it represents the various actions of magnetizing the stator and the core itself. Yeah. So because there is no alternating current, you do not experience any capacitance or inductance. You do not experience reactance. So these elements are out because of not having the alternating parts of the supply. Okay. So in essence, we will be establishing the value of R1 from doing the DC test, because it is the only element that will be present in this configuration, right? So what we will now do is, in order to carry out the test, you will then have a variable voltage supply that will slowly raise the voltage that is passing through the circuit until a point whereby your elements are not overheating. Remember, the load is not passing through. You're not, in this case, your motor is at a standstill and it is not operating in its normal modes, okay? Applying a DC voltage to an induction motor is not the usual method of operating the motor, yeah? So we will have to be careful with the amount of current that we allow to flow through the windings so that they do not get burnt, okay? That's why we use a variable voltage supply, so that you can take it up to a point whereby you are not burning or you're not overheating the motor due to too much current flowing. So what will happen is, we assume that these resistances are all equivalent, okay? Now, what you will then do is, in this circuit, what you have is, you have the voltage DC is equal to the current that is flowing through it, let's call it I1, times R1 plus R1, because these are identical to each other. Now, what are we looking for? We are looking for R1. So we rearrange the circuit so that it is R1 is the subject, and you have VDC over I1 or IDC times 2, because you had 2R1 here, the 2 now comes to that side, right? So straight away, we have established a way of getting the initial circuit element, which is R1. So let's highlight it, that we now have a method of obtaining it. Any question? Okay, let's look at method number 2. So now method number 2, which we mentioned, is called the no-load test. So the no-load test can be used to measure magnetizing impedance, as well as the rotational losses that you get. Let me just let somebody into the class. So we move on to the no-load test. So the no-load test now is applied using the circuit that you're seeing there, okay? So we have, first of all, on the left-hand side, you have a 3-phase power source. So in this case, when we say no load, we mean that we will run the motor without any load attached to it, so that the only effort that the motor has to make is to overcome its own weight. That is the weight of the rotor and the kind of resistance due to magnetizing itself, the losses that you use to magnetize the rotor, or to transfer power from the supply to mechanical power available at the shaft. Okay, so this voltage is applied here. It's a 3-phase power source with variable voltage and also variable frequency. We use variable frequency because we would like to get, remember that the synchronous speed, the speed of rotation of the magnetic field is determined by the frequency. So if you have full rated frequency, you will then also tend to have full rotational speed. And we want to be able to control the rotation so that it doesn't run away from us, or it is not too fast. In addition to that, frequency is a main component, or it is a variable within the impedance, the reactances that are there. Yeah, remember the reactances are given by X is equal to 2 pi FL, all right? So the inductances that we have inside there are affected by the frequency. So we want to keep them measurable. So if we keep this low, we can also have kind of a lower reactance that is measured at this testing phase. Okay. So the no load test is given by that circuit. So you have power meters, so you're able to check what is the input power at no load. You're able also to check what is the voltage at the terminals at no load. And also through the ammeter, you're able to get input current at no load. Sorry, at no load, right? And from this no load current is obtained by getting the average of all currents flowing into the motor when it is running on no load. So you have IA, IB, and IC, which are averaged together to get your line currents, or no load line current. Okay. Now, one thing that we will need to note from this is we have voltages, or rather we have powers that are flowing through. And we remember we said that we had the air gap power being equal to rotor copper losses, plus the converted power. And we were able to modify our equivalent circuit such that instead of having one element, we have now two elements which represent the rotor copper losses and the converted power. We split those for purposes of our estimations of voltages here, or of the elements that we are looking at. Everything else remains as it was in the original equivalent circuit. Okay. Now, what happens next? When we are having these elements in this configuration, you can then say that you have a slip that is, or rather we can look at the slip. Now, when you have no load, when there is no load applied, it means that all the power that is passing through from the input side, a majority of it will reach the converted side. Why is that? Our slip tends to be very, very small, 0.00 something, right? Such that in this particular instance, when there is no load, yeah, our value of slip, which is very, very small, and it is given by ns minus n over ns. If the mechanical speed is very near to this speed, our slip tends to be very small. That is, the difference between the two of them will be very, sorry, it's not actually the slip that is small. It is actually the difference between the two, such that when you look at 1 minus s over s, which is extremely tiny, it will be a very high figure. So this converted power is a very high proportion of what is there, and the rotor copper losses on this side is a smaller proportion of the same. Because of that, we then say that R2 is much, much less than R2 into 1 minus S over S, because this figure is in the thousands. Okay, so it is much, much bigger, and therefore this one tends to, the impact of this tends to be much less than the impact of the other one that you have here. So first of all, the impact of that is far, far reduced. Similarly, X2 has the same effect. This element, the converted power, is much bigger proportion than what you have. So in that case, you can reduce or remove that X2. So what does that mean? When you remove those two, you're left with this now final circuit for no load test. Okay. Remember, we've removed X2 and we've removed R2, and you're left with this element. Okay. Similarly, we have these arms that are here, which are represented there. Okay, it's just a slight redrawing of what we have discussed. Okay, now let's look at this circuit in more detail. Okay, this element that is here, you can see we are tending to call it RF and W. These are representing, so the converted power is feeding what? It is feeding friction. It is used to overcome friction, and it is used to overcome windage losses. That is the resistance due to air, the movement of air, or rather the movement of the rotor through the air. Okay. All this converted power, because we have no load being connected to the motor, all the converted power that you have is being used up to get rid of to overcome friction and windage losses. Okay. Now these resistances are in parallel with each other, right? And remember, we had said earlier in a previous lecture that in some cases we tend to shift these core losses to the other side of the diagram. This is now the reason that we were talking about on that side, that we have resistances that are overcoming losses or overcoming non-useful components of the operation of the circuit, right? Those are now on the other side. So let's say we lump those together as well, right? Now, once we now look at this circuit in the way it is flowing, okay, you would say you have your input current, and your input current splits into three possible arms. What we tend to see is that in this case, when you have a no load situation, the majority of the value of the current that is flowing through here will tend to flow through this arm of magnetizing. The bulk of your power that is being used in the circuit is actually flowing through and being used up in magnetizing the circuit, because friction and windage are actually fairly small. Remember, we eliminated the load, first of all, okay? So the load, I mean, is a very high aspect of the motor. The whole purpose of having a motor is to drive a load. If you remove the load, you're left with friction and windage and various other aspects of resistance over here of the windings and the magnetizing current. So eventually what you will see, if we were to look at the equivalent circuit, all right, looking at the voltage or the circuit from that point of view, the voltage that is here and the current that is there, right, they would give us an equivalent impedance given by voltage phase over input no load, current no load. And this equivalent impedance tends to be, the majority of it is actually equivalent to X1 plus XM. The majority of the impedance that is seen by the supply is taken up by X1 and XM, right? And we also know from our previous discussions that R1 is only the winding resistance. It is a minimal element within the circuit, and that is why you're able to reduce it or eliminate it from the circuit. Okay, so we find that we have reduced that resistance because it is much, much less than the values of the reactances. And we have removed these ones because they are comparatively less when you have no load, or they take up less of the current when you have no load being applied to the motor. Okay, your primary path will be through there, right? So now we've already established, we've now come towards some more elements, albeit as a sum of each other, but hopefully we will be able to separate them out using the final circuit that we are going to look at, or the final element that we are going to take a look at. So let's look at the locked rotor test. In the no load test, we were allowing the motor to run freely without any load being applied to it. When you look at the locked rotor, the opposite happens. We apply a brake such that you are powering the motor, but the shaft is not free to rotate. You have locked the rotor. So what happens in this case? You are supplying power, but the power has nowhere to go. And what would be the impact of that? Let's look at the impact of that. So we have the same setup, an adjustable three-phase power source. You have power meters, voltage meter, and current meters. Current is obtained the same way as we had before. We have an average current, which is equal to IA plus IB plus IC over 3. Okay, so this is an average current. Average current, right? Now, once again, the source that we have, we start it off from a 0 voltage and a 0 frequency, 0 hertz frequency, and we slowly increase the voltage and the frequency, bearing in mind that we don't want to burn out the windings that are within the motor, okay? We don't want to burn out the windings, so we limit the amount of current that is passing through the motor, and that is tracked using the ammeters that are supplied there. Now, in this particular case, slip is equal to what? It's equal to ns minus n over ns. In this case, n is what? It is 0. Okay? So if our mechanical speed is 0, because remember we have locked our rotor. If our mechanical speed is 0, that means our slip is 1. Okay? So if we look at our equivalent circuit again, the original equivalent circuit, we then tend to have a situation whereby you have this variable S is equal to 1, so that you have the R2 being the only element on that side, or R2 being a very small value. Yeah. Remember, in usual terms, R2 over S is a large value, and we would have R2, the rotor copper losses, and the converted power as both elements of this. However, because slip is 1, you are left with R2. You cannot split it the way we had split it before over here. Yeah, these two elements don't come into play. In fact, this one now ceases to exist. You're left with only an R2, okay, because we have the original equivalent circuit, right? So that now becomes an R2. What does that mean? It means that in this case, because your resistance is very low, right? There is no slip, the slip is 1. So there is no slip that is kind of magnifying the value of this element. So because this is very low, yeah, this arm has a low impedance. What does that mean? If you have our input current I1 coming and splitting into I2 and IM, because this arm or this path has low impedance compared to this path, the majority or the bulk of the current will tend to flow in that wing, and the impact of this will be much, much reduced, right? So in fact, we tend to ignore, because the impact of this low impedance being there is that IM tends to be 0, and the impact of these are reduced. So what actually happens is you then have a simplified circuit which has only 4 elements, that is R1, X1, X2, and R2. Remember, we already got R1, and we had a type of, a kind of one way of establishing X1. So we would be left with X1 and X2, okay? Now, that would mean that you have a circuit, that looks like that. Okay, with our V phase and our I1 or I, let's call it locked rotor. Okay, R1 is still there, X1 is there, X2 is there, and you have R2. Remember, S is 1. You already know R1, so you can be able to calculate R2. Those would be identifiable from there, right? So you have your Z locked rotor is equal to R locked rotor plus JX locked rotor. Now remember, here we have adjustable frequency and adjustable voltage. Now we are operating at a reduced voltage, yeah? So these values of reactances are not the rated values. They are less than the rated values. That means that our XLR here, which is equal to JX1 and JX2, is kind of a prime value. It is different from the original. So XLR prime, which is equal to X1 prime plus X2 prime, will be different from the original. In order for us to get the rated value of XLR, we will then have to take into consideration the frequency that is being given. In which case, for us to get the true rated impedance, you do that conversion, right? Because our rated frequency probably will be 50 hertz, probably, and our test frequency can be low 10 hertz, and so on and so forth. So you have to take into account those differences when you're doing your calculations and tests and checks. Similarly, R1, we have already talked about it. We know that RLR is equals to R1 plus R2, but we know R2, we know R1, so RLR is equal to, RLR minus R1. So you're able to find R2. Okay, so we've established now enough of the elements so that we can be able to work out some of their variables. Now, note that our XLR is kind of giving us two values. It is giving us two variables in this case, okay? What we usually do with this information is we take into account the design. So there are characteristics of the designs of the rotors that are known, and they give the relationship, between X1 and X2 due to how the rotor has been designed. So these are various types of designs of motors, standard types of designs of motors that will enable us to know the ratios of X1 and X2. So you have design A, B, C, and D. Those details can be found in the text. The text, I believe, is available on the Google Drive, and you can be able to see more about how we get these different ratios. So those are the ones, that is how they are taken into account. So now let's bring all of these tests together to form now a full picture of what the equivalent circuit is and how we can obtain the values that are available in the equivalent circuit. So just a second. Just give me a minute here. Okay, so we have an example here. Let's take account of all of the tests that we've looked at. We've looked at 3 different tests and what they establish. So essentially we have a 3-phase 415 volt 50 hertz 4-pole motor, which is star connected with a rated current of 28 amps, and it has test results as listed. Okay, we start with a DC test which gave those values. Take note of what we've said. We said the rated current is 28. So the maximum that the machine can be able to take would be at 28 amps. If we were to apply the full voltage of 415, it would be much, much higher than the 28 amps. That's why we reduce and we start with a low value of the DC test of 13.6 volts. Okay, that same 13.6 volts gives us 28 amps, which is the rated current that we are looking at. Likewise, the no-load test. No-load test, we are able to apply the full voltage with the full frequency. However, we get low currents that are being seen from there. Locked rotor test, remember this one now you are creating a resistance. The rotor is not free to rotate. So you will tend to have a much lower voltage being applied and a much lower frequency so that you don't exceed the limits that we're talking about, 28 amps, which was there. So in order for you to do that, you will result in lower currents being seen. Okay. So let's get straight into it. The first thing we calculated was in the DC test, we were able to get R1. So R1, we established that R1 can be found from the DC test by doing VDC over 2 times IDC. So in this case, it is 13.6 over 2 times 28. So with our calculator, 13.6 divided by 2 times 28. Okay, so we've established that the first resistance 0.243 ohms. Okay, so our first element has already come into place. So let's kind of draw it over here. So R1, we say 0.243. Okay. Let's look at what we can establish from the no load test. No load test. Right. Now, for the no load test, we said that we apply a voltage and at a certain frequency so that you get various currents. So now these are the currents that we found within the no load test. So the average of them, average of the no load, is given by 4.2 plus 4.1 plus 3.9 divided by 3, which in turn gives us 4.1 you get 4.067 amps. What does that tell us? Our impedance at no load is given by our phase voltage. Now, phase voltage is not given. We are given line voltage, so you have to convert it into phase voltage by doing it like that. And then you divide it by the no load which is so that gives us 176. Okay. Sorry. Gives us 58.9. It's not amps, it is ohms. Okay. Next, we look at the stator copper losses, which we can calculate from up there. These will help us to get the rotational losses. So the stator copper losses are up there, and they'll be given by 3 times the current at no load times squared times R1, which we have already established before. And so this is given by 3 times 4.067 squared times the resistance was 0.243. And that in turn gives us 12.05 watts. Now, these are the stator copper losses when you have no load. Now, these will vary. However, what we can use from this is our rotational losses. Remember, we said the input power, this V, in this particular test, it is derived, or rather, it is representing our converted, not our converted, our air gap. Okay. But because certain elements of the circuit are not present, it can be taken as a whole. And that one is equal to stator copper losses, or rather stator copper losses plus the rotational losses. Remember the rotational losses we've talked of, we are combining friction and windage, and we are also combining the core losses from the stator side. So this particular element combines all the non-resistive power losses that we encounter, okay? And this is useful because the rotational losses here do not change regardless of the level of current that we are supplying. These are fixed losses. So if we establish them using the no-load test, these are fixed losses that we can make use of regardless. In the previous examples that we've looked at, we've always talked of rotational losses are, 1000 watts or whatever it is. The reason that they are fixed is that they are independent of the current. And once you establish them using this test, you can make use of them in whatever scenario. So in this case, we will try to look at what are our rotational losses. So they are given by the input minus stator copper losses, which we've just calculated. So our input at this point is 420 minus our losses over here, which are 12.05. So it is 420 minus 12.05, which gives us 407.95 watts. Okay. So now let's look at what we can learn from the locked rotor test. Okay. Now, in the locked rotor test, we had the elements being given here. So we have to get, first of all, the average input current. So locked rotor current average is given by 14.1 plus 14.0 plus 13.6. That gives us 41.7 divided by 3, which is the average. You get 13.9. 13.6? Yes, 13.6. 13.9 amps. Okay. So what is our impedance during locked rotor? It is our voltage, which is 50. Again, this is a line voltage, so you'll divide it by √3. Divide it by √3. So it is 50 divided by √3 times your current, which is 13.9, which gives us 2.077. Or let's call it 2.077, yeah. Just check on this side. Something on the chart. Okay, 2.077 ohms. And that is our locked rotor equivalent impedance. Okay. Now, from this, we now get other aspects of the circuit. We can get them from now trying to get this impedance. It contains resistances and reactances. We want to split those. So we split those by calculating the impedance angle, okay? So that we are able to determine what part of this is resistance and what part of this is reactance. So we start with, let's call it theta. So theta is equals to the inverse cos of the input during locked rotor over √3 times voltage locked rotor times the average locked rotor current, right? This is standard. This derives from, you have your power, let's say S, is equals to the power times cos theta. And this power is 3VI cos theta. And remember, if this is a phase, it will become √3 times voltage, because this requires a phase voltage, okay? So that's the derivation of that one. So let's look at it in terms of the actual figures. So we will have input, what locked rotor was 920. We have it there, 920 over √3 times, I think it was 50. Yep, it's 50 times the current we have just calculated, which is there, that would be 13.9. So this is 40.16 degrees. So this is the angle, just to remind ourselves, this is the angle between, if that is your S, you have P and Q. So that's the angle between the two, okay? Where P is real and Q is imaginary, right? So now let's make use of this. So we say ZLR is equal to RLR plus XLR. And remember, the XLR is a prime. We had said that because of the reduced frequency, XLR there will be a prime. So now RLR here is given by 2.077 cos theta, which was cos 40.16. So this gives us 1.587. Right now, RLR from our circuit, which was here, our locked rotor circuit, we said that RLR is R1 plus R2, but we've already calculated R1. So we want to get R2 from this. So let's make use of that. So RLR is equal to, R2 is equal to RLR minus R1, which is 1.587 minus, all the way at the top, 0.243. it is 1.344. Okay. Let's now move on to XLR. XLR prime was given at 15 hertz, and it is equal to ZLR sine theta, which will be 2.077 sine 40.16, which is 1.34 or 34. Okay. Now remember, this is XLR prime. So we want to get XLR without the impacts of the prime, which we had said that is gotten from, again, that formula, the rated over the test times so rated is 50. Is it rated is 50? Test is 15. Rated is 50 over 15 times 1.34, which gives us 4.467. Okay, so you have your R2 and you have your XLR. Now XLR, remember, is X1 plus X2. It's a combination of the two. Now, in this particular case, let's assume we were looking at what we had talked of, design A, B, or C. Let's say we are looking at a design B. So if you have a design B, X1 is equal to 0.4. X1 is equal to 0.4 XLR, and X2 is equal to 0.6 XLR. That gives you 0.4 times 4.467, and that is 0.6 times 4.467. .78. And this is 2.68. Okay. So we now have most of the values that we are talking about. So X1 is 1.787. X2 is 2.68. We get XM. So XM can then be established using the formula. XM is given by Z of no load minus X1. Remember, during that, when we had no load, we had said that when we had this no load, we had talked of the majority of the only impedances being there are this and this, and we said that the bulk of the current will pass through that path. So we have Z in terms of impedances being X1 plus XM during the no load. So that can allow us, if we know X1, we can then get Xn. So that would mean Z no load minus X1, right? Which gives us 58.91. Sorry, where was Z and L? Z no load 58.91 minus 1.787, which means Xm is equal to 57.123 ohms, which we input here. And our R2 was 1.344 over S. Okay. It looks like that, right? So we have thus been able to establish from the tests that we've done, the 3 tests, we can then establish all of the elements that we've talked of. Notice that the core resistance has been eliminated because we have put it into the rotational losses. So we have now constructed the format that we had in the previous ones, which would allow us to establish things like maximum torque, starting torque, power transfer, and so on and so forth. So let's work out as we are right now, what is the maximum torque for this particular circuit. So wherever you are, just work that out. Let's see what we have within the chart. So we start with Thevenin voltage, Thevenin resistance, and Thevenin reactance, and so on and so forth. So let's have those coming through in the chart. So those are the values for Thevenin voltage and resistance and reactance. Please work through, go through to the maximum torque, find the maximum torque, and also find the starting torque based on this. So you can do a bit of practice in the text. Make sure you have familiarity or you're conversant with the power flows, the torque slip characteristic, and also this derivation or this determining of the circuit parameters from the motor tests, the 3 motor tests that we do. I believe the motor tests will be part of your lab work. If I'm not wrong, there should be some lab work going on that should be in parallel with this. So I guess you'll be able to see the practical aspects of actually determining these parameters. So essentially, this is the main elements, or these are the main aspects of three-phase induction motors. What remains now from here is we will now look at various other aspects of motors. So we look at essentially, we have aspects called circle diagrams. Circle diagrams enable us to determine these characteristics and how to note how and to do an analysis of how the motors operate. We will also look at starting of three-phase induction motors, braking of three-phase induction motors, and speed control of the same. So that is what we will cover for the remaining elements of three-phase induction motors, and that will take us through to the end of this month. I think we have 2 more lectures before probably there's a break. Then in January, we can look at single-phase motors. These include induction motors, single-phase, and universal, and also what we call shaded pole. And I think in one of the classes, somebody had a question about universal motors. We will cover that early next year in January, right? So for now, thank you very much. Next lecture will be on Wednesday next week. I will confirm as we get closer to that, so probably Wednesday, right? Thank you very much, and have a good afternoon. You have the same answer for R Thevenin, but not X Thevenin. Check, check. Wambua Michael. Thanks. Okay, that's the end of the class.